okay guys, you're going to use your periodic table, which there is one on the very back page, so make sure you utilize that. But beryllium. So we know that the atomic number is the number at the very top of each of the little tiles. We also should know that the number of protons equals the atomic number, and it also equals the number of electrons. So whatever this number is, you're going to have 4 protons and you're going to have 4 electrons. And by looking at this, I know that this is on the left side of the periodic table, which is where my metals are, with the exception of, of course, hydrogen. Valence electrons, this is going to be the group number. So this tells me it's the little the A number that's there. So it is in group number 2. So this has 2 valence electrons. Remember, the first energy level can hold up to 2, and all of the others can hold up to 8. The number of orbitals or shells or energy levels, however you want to call that, it tells us the period. So by looking at that, I am in period 2. So that tells me that I have 2 energy levels. The next one does not tell me what it is, but I know, again, that by knowing the number of electrons, I know the number of protons, and I know that the atomic number is also 14. So by looking at number 14, that tells me that I am silicon. Silicon is located along that stair step, so that is going to be considered a metalloid. In fact, that is what is in all of your cell phones right now is silicon. They make computer chips up for it, or out of it. This is also in group number 14. So group 14, which tells me right under there, it says 4A. So I've got 4 valence electrons. It's that little A number there. Number of orbitals, I go off to the side. These are the ones that go from side to side. It's going to be 3 is the period 3. That tells me that I have 3 energy levels or energy shells. All right, here I have atomic number 10, again, because all of these will always be the same. Number 10 is going to be neon. Neon is in group number 18, so I'm going to put that over there. What's great about group 18 is that it has 8 valence electrons. That means it is full, so it is non-reactive. It is on the left side of the periodic table. It is considered one of our noble gases, so it is considered a non-metal. It is in period 3, so again, 3 energy levels there. And lastly, I have number 13, so I have 13 is my atomic number, 13 electrons as well. And number 13 is aluminum or aluminium. Aluminum, this is right below the stair step, but this is the only one that is not considered a metalloid that is on the stair step. So this is actually considered a metal. So this is what all our soda cans are made out of. Aluminum is a metal. It is in group number 13, which means that I have 3 valence electrons. And I am in period 3 as well. So again, 3 energy levels. So what we know here is that we're looking at the atom's identity. It is the number of protons that determine an element's identity. So, which is why all of these numbers here, atomic number and protons, are the same. Later, when we deal with bonding and stuff, we know that we can give away electrons, but in most cases, all of these are the same. But if we ever change the number of protons, it will change the element, which is what happens on stars. That nuclear fusion, the hydrogens, 2 hydrogens fuse together to make helium. The atomic number increases, going from left to right on there, and the atomic number equals the number of protons and the number of electrons. So you've got 10 atomic number, you got 10 protons, 10 electrons. Your mass number is going to be your atomic number. Mass number is going to be your atomic number minus your atomic number is going to be the is going to equal your neutrons. We always would say mass equals protons plus neutrons. I would like y'all to do it this way versus this way, because yeah, it just works out a lot easier that way, because we know that all of the mass is located inside the nucleus. All right, elements of the same period have the same number of, again, energy levels, shells, orbitals, energy shells, however you want to, whatever you want to call it. It's got a lot of names. Elements in the same group have the same number of valence electrons. So these are often called families. This valence electrons is like equal to their DNA. So they react the same because they have the same number of valence electrons and react similarly.
Okay, here we have listing the 5 pieces of evidence that show a chemical reaction has occurred. We actually taught you guys 6. We taught you a little saying, which was city girls love their cell phones on. To help you remember the 6 signs of a chemical reaction, that first C is simply for chemical reaction or chemical change, so that's not really one of the signs. So we start with G, that G stands for gas. And we have L, which is for light. T is for temperature change. C is for color change. And P is for precipitate. And a precipitate, remember guys, is when you have 2 liquids or a liquid, and that liquid goes through a chemical change, and it's the formation of a solid from a liquid. Like when milk sours. When you have your milk, you're sitting it out, and you don't add anything to it. You just leave it. Eventually, it's going to become solid and become very chunky. And then, of course, the last one there's not space here for is odor. We also see odor when milk goes bad. If you've accidentally smelled sour milk, you know that it's not a pleasant odor. Sometimes the odors are good, like when you bake cookies or bacon. Temperature, color. The big thing of these, you guys, you need to remember that it's the unexpected. If we add food coloring to water, it's going to change color. That's not a chemical change because that is expected. So when we're looking for these changes, they are going to be the unexpected changes. And the last little piece of advice, guys, you remember dissolving is not a chemical change. You guys get tricked by that a lot. If you dissolve sugar in tea, there is still sugar there. You still have the same substances. You still have your sugar, you still have your tea. They're just mixed together. That is not dissolving. Okay, let's come down to this chart. Here we are IDing the number of elements, molecules, and atoms in the compound below. Here we have 3Al, 3SO4, 3. So the first question, number of elements, we're going to look for the capital letter. Capital letters. Here we have a capital A, capital S, capital O, so we have 3 elements. The number of molecules comes from this coefficient right here. That tells us the number of molecules, the number of copies of that particular molecule that is all put together, so we have 3 of them. The first element here we have is Al. And how many Als do we have? Well, Al3, this little 3 down here, you multiply it times the coefficient. It's not in parentheses, so we don't have to worry about that. So 3 times 3 is 9, which gives us 9 atoms of aluminum. Then we have our sulfur. Our sulfur is in parentheses. There is no subscript behind the sulfur, so the parentheses is the first one that counts. You have to multiply 3 times 1 to give us 3 sulfurs. And we can't forget to multiply times the subscript. 3 times 3 gives us 9 sulfurs also. And then we have our oxygens. Our oxygens, there is a subscript of 4. We first multiply times the parentheses. 4 times 3 is 12. Then we have to multiply that times our coefficient. Everything gets multiplied times the coefficient. So 12 times 3 gives us 36 oxygen atoms. The second one, we have first count the capital letters. We have a capital M, capital C, giving us 2 elements. How many molecules? Molecules comes from the coefficient. The coefficient in this molecule is 4, so there are 4 molecules. We list our elements. We have first Mg and we have Cl. Now let's count our elements. There are no parentheses. We don't have to worry about that. We have the subscript of 2 after the Mg. We multiply that times the coefficient of 4, giving us 8 magnesiums. Then we have chlorine. Chlorine has a coefficient of 3. 3 times the, a subscript of 3. 3 times 4, giving us 12. And then there is not a third element here. Going down to the next one, we have how many capital letters? 1, 2, 3. There are 3 capital letters. Number of molecules comes from the coefficient, so there are 12 copies of this molecule. The elements, we have potassium, phosphorus, and oxygen. Now let's count them, no parentheses, so all we're worried about is our subscripts and our coefficients. Potassium subscript is 3. 3 times 12 is 36 potassium atoms in that molecule, in that, that group of molecules. Then we have the phosphorus. There is no subscript behind phosphorus, so that would be a 1. So 12 times 1 is 12 phosphorus atoms. And then we have 3 behind the oxygen atom. 3 times 12 is 36 oxygen atoms. And finally, we have MgSO4, giving us 1, 2, 3 different elements. No coefficient in front of it, so there is only one molecule of this compound. And then the element, we have, of course, magnesium. There is no coefficient, there is no subscript, so it is 1. Then we have sulfur, no coefficient, no subscript, 1. And the last one, oxygen, no coefficient, but there is a subscript of 4, so it would just be 4.
Okay, here we're filling in the chart with the particle information. So here we're moving on to atoms. So we know that our protons are positive. These are our positive guys. They are located inside the nucleus, and club nucleus are allowed to come in. And their mass has a mass of 1 AMU. They made it simple, just made it 1. Our neutrons, this is where we have to be careful. These are neutral, meaning they have no charge. They are also with the protons inside the nucleus, and they also have a mass of 1 AMU. Our electrons, these are our bad guys. Our electrons, I think of it like being electrocuted. That would be a very bad thing. And these are not in our nucleus. They are in the electron cloud. So they orbit at the speed of light around the nucleus. And they're so tiny. They say basically these are 0. We don't even count these in our mass. So all of our mass is located inside of our nucleus right here, which is where we get the formula that our mass number equals protons plus our neutrons. All right. According to the law of conservation of mass, how much oxygen is on the reactant side? So the law of conservation of mass says that matter can neither be created nor destroyed. So matter cannot be created nor destroyed within a chemical reaction. So this side, our reactant side, please make sure that you know that these are the ones that react together, and this one's our arrow. So we said this one was R, our arrow is A, and then over here, these are our products. So we said RAP, R-A-P, reactant arrow product. Our reactants have to equal our products. So if we've got 4 grams of hydrogen here, and we don't know how many oxygens we have, but they have to equal 36 grams of water. So that tells me that I have 36 minus my 4. Okay, is going to be 32. So because 32 right here, if I put 32 plus 4 equals 36, I'm golden. So I've got 32 grams of oxygen.